In this problem, we're looking at a quarter car model where we are trying to track the chassis represented by the mass when the input into the system is z, which is actually going to be a displacement or the height of the road that the car is traveling on. We're going to see that this is a multi-degree of freedom system. We have the mass, which is able to translate up or down, connected to spring K1 and a damper C, and it's attached to what will be a node where it's attached to another spring. So the lower spring, K2, is meant to simulate or replicate the tire, which is able to flex and store some energy. And then K1 and C are meant to be the suspension of the car system. So we want to see how does the chassis move depending on the height of the terrain that's traveling over, where that height can change in time t. Now, where this is different from the previous example is going to be in the type of input we have. Our input is, for the first time, a displacement rather than a force. And we'll see how that is reflected in the free body diagram, and then the equation of motion, and then the transfer function. So ultimately, what we're trying to find here is the transfer function. I'll again call it g. That's going to be the chassis displacement x over z, which is the input displacement, the height of the terrain that we're traveling on. As with mechanical systems, I want to start with my free body diagrams. And here I'm going to have two free body diagrams. I need one of the mass, since it has a degree of freedom x, and the node at w. Because the node at w is attached to the mass through, well, a spring and a damper, it can move independently of the mass. I can hold the mass at 0 or not moving, but I can move the node, and that's okay. I can hold the node steady and move the mass up and down, so x and w are independent degrees of freedom. Here z is going to be a displacement, but we're going to see that in these type of systems where we have a prescribed displacement or an input displacement, we do not want to draw that node in our free body diagrams. So let me start with the mass, which is connected to degree of freedom x. We have the forces that will act on it. It can only translate up or down. So according to here, the only elements directly touching M are K1 and C. And I can go right now, and to help us out, W is going to be our second degree of freedom, and that's our node with our inertia picture and our force picture. So I'll just draw that now to help us draw the free body diagram. So starting at the top with free body diagram 1, and then we'll move on to 2. Mass is attached to K1 and C. Both of those in turn are attached to W. So the top of both of them is at X, and the bottom of both of them is at this W. So drawing in tension down, we have K1 and we have C. So the force in the spring is going to be the net displacement of that spring. Again, the top is attached to X, so that can translate, and the bottom can translate as well. So what we want to think about is, if we were to hold one side at 0, does a positive or a negative value on the other degree of freedom cause tension? So let's say we hold X at 0. Will a positive W cause tension or a negative? In this case, if the top is held still, a positive W will cause the spring to go into tension. So W is positive. And then in the opposite way, if W is held at 0, so we're not moving the bottom, a positive X will cause compression, the spring will shorten, but a negative X will cause tension. So we get K1 W minus X should be the force when we are assuming tension in the spring. And I'll rewrite this so it's a little bit clearer. K1 W minus X. And if we look over to the damper, we want really the net velocity of the ends of the damper. If they're both traveling the same velocity, the damper is not being stretched or compressed. So here, a W dot that is positive if we hold X dot at 0, so the top of the damper is not moving, but W dot is. W dot positive causes it to stretch, causing tension. So W dot positive, and then we'll have a minus X dot. So really for the same reasons as the spring, that x dot negative, the velocity of the mass, is upward. If W is held at 0, that damper is going to stretch and it will be in tension. So positive W dot, a negative x dot. And those are the only forces that act on the mass that we are accounting for, the spring, the K1 spring, and the damper C. And then we have the inertia mx double dot. That's the full free body diagram for the mass. Now we can move on to the node where K1, K2, and C all meet. We'll have, if we assume tension again, equal and opposite forces from the K1 spring and the C damper. And once again, we already know what their values are. They have to be equal and opposite as they were in the first picture, because I'm assuming tension in both. So that's done. Then I have the force from K2. Notice the node is attached only to K1 and C and K2. Now, what is the force in the spring K2 going to be? Well, this is where it's a little bit different than what we saw before. If I look at the two ends of K2, I have the top is at W and the bottom is attached to Z. Again, Z is a displacement in this case, not a force. So the displacement Z2 is here going to figure into our calculations, because we need to think of the same way we did K1, how is K2 stretching? So for example, if I hold W at 0, the way that the arrow is pointing, a positive Z causes tension. And if I hold Z at 0, a negative W causes tension. So the force through this spring is K2 Z minus W. And that's it. Z itself, by itself, does not appear in a free body diagram. It is not a force. Once again, we see it indirectly is included because it is going to be in that force calculation for the spring K2. But Z is not directly acting on anything because only forces are in free body diagrams, and Z is in the force of the spring. On the right-hand side, we have the node, and there's no inertia because we ignore the mass of the node, or we neglect it and say it is 0. Now, as an aside, I could, in principle, draw this node at the bottom here as a third free body diagram, but I actually don't know enough information about it. I know that it would be attached to K2 at the top, would be Z minus W, but at the bottom node, there actually is, in fact, some force that is pulling it up and down, because that displacement Z must be caused by a force, or vice versa. But I only know what the displacement is, I don't know what the force is. So there should be a force here, it is not Z, it's something else, but I don't know what it is. So I can't actually draw the free body diagram of that bottom node, and I also don't need to. So 1 and 2 are going to be enough here. My free body diagrams are done, so I can move on to my equations of motion. And my first one, I am going to start by summing forces in the x direction in my first picture. With the direction of x, I have the arrow pointing down from the spring, which will be K1 W minus x. And also pointing in the same direction, I have the tension from the damper, so that will be plus C times W dot minus X dot. And on the right-hand side, I have the inertia, again pointing with the direction of the degree of freedom, mx double dot. That's my full first equation of motion from the first free body diagram. Moving on to picture 2, I will sum forces in the W direction. So in this picture, the force from the spring is up, so in the negative W direction, so I have a negative K1 W minus X, and also the damper, a negative C W dot minus X dot. And here I have a third force. It goes with the direction of W, so it will be a plus K2 Z minus W. And my right-hand side, my inertia for the node is 0 as we are neglecting the mass. Two equations of motion from the free body diagram. Now I'm going to rewrite them just a little bit. So in one, I want to distribute the K1 W minus K1 X plus cw dot minus cx dot equals mx double dot. This will make it, I think, a little bit easier when we do the Laplace transform, which actually I'll do now. To go from 1a to 1b, this is where I'll do the Laplace. And keeping in mind in this problem, everything started at equilibrium, so all of my initial conditions are 0. So going term by term, the first one, k1 is a constant, it comes out, little w goes to big W. Minus k1 is a constant, little x goes to big X, plus cs big W. And then I have minus cs big X. So these s's are coming from the w dot and the x dot when I do the Laplace transform. But all the initial conditions go away because we start at equilibrium. On the right-hand side, I get an ms squared big X when I do the Laplace transform of the right-hand side. So 1b I will put aside for now, because if I look at it, I have x, I have w, but my input is z. So remember, what am I trying to find? This transfer function x over z. This has an x, but no z in it, so I definitely need more equations. Now I'll move on to equation 2, which I will first rewrite as 2a by doing that same distribution of the constants, so negative k1w plus k1x minus cw dot plus cx dot plus k2z minus k2w equals 0. And as with the previous one, I'm going to do a Laplace transform of both sides. So going term by term, I'll get a negative k1 big W, and that will be a plus k1 big X minus a CSW plus a CSX plus k2 big Z minus a k2 big W equals 0. And if we look at 2b, I now have x and w and z in this equation. So the problem with only using 2b is there's too many unknowns to get just x over z. So let's count our outputs and our inputs. So outputs, we have x and w, and the input is the displacement z. So at this step, it doesn't matter mathematically if z is a displacement input or a force input or coming from a non-mechanical system, because we are in Laplace transform, we're just in math mode at the moment. It was in the free body diagram step where it mattered and made a difference, was it coming from a force or from a displacement. Counting our outputs, x and w is 2, and between equations 1b and 2b, we are going to be able to get our desired transfer function. 2 outputs, 2 equations, 1b and 2b, for our 1 input of z. Now I'll use Mathematica to get our desired transfer function. And in fact, we'll get both transfer functions along the way. So equation of motion 1 from 1b, k1 big W minus k1 big X plus CSW minus CS big X equals ms squared x. And notice I'm putting spaces between everything, and it understands that to be multiplication. So k1w minus k1x plus CSW minus CSX equals ms squared x. And if we run that, we can suppress it. Equation motion 2 will be 2b minus k1 big W plus k1x minus CSW plus CSX plus k2 big Z minus k2w, and the right-hand side is 0. All right, so both equations of motion are now in. Just double check that it's all correct. Negative k1w, k1x, a minus CSW, a plus CSX, a plus k2z, and a minus k2w. Now let Mathematica take over and do the algebra for us. So solve, we have these 2 equations of motion, and for the outputs of x and w, z is once again our input. So we get x, we get w, and I'll clean this up just a little bit here. All right, so we have an x expression with a z on the other side that we will be dividing through for the transfer function, and a w where we'll also be able to divide through by that z. So my transfer function, I will call it, I guess I'll call it g to match what I have on the paper. This is my x over z. So that equals, and I can take this expression and copy it. And because it's x over z, I'm dividing through by the z, and that's what g is. So it's not quite in the form that I want it. So what I can do is, same thing I did before, is I want to express it using this collect function. And we have to do the numerator separately from the denominator. So I want the numerator of g and collect on s. And then the same thing with the denominator. All right, so now it has grouped the coefficients in front of the s terms, and we have on the bottom, we have an s cubed, a squared, an s to the first power, and that constant. And then we have our numerator, which has an s and a constant there. So this is in the form that we want it pretty much. So the only thing is going to be when I rewrite it, I always want descending powers of s. So that will be my last step. Now writing down that final transfer function g is the x over z. I did not care in this one about y over z, although Mathematica did give it to us if we had wanted it, is going to be equal to, remember, descending powers of s. So I do have to just be cautious when I rewrite this that it's descending. So c k2s plus k1 k2, and now I have to reverse the denominator as well. So the s cubed will come first. Then I can factor out that m if I want to. So m times quantity k1 plus k2, and that's s squared, and that's being added, plus the s term, plus k1, k2. So this expression, this x over z, is the transfer function written in the standard form that we want, descending powers of s with our coefficients grouped together. This is the transfer function that we were looking for. And as a quick recap, where did this come from? It's a mechanical system, so we are going to get our equations of motion and then our transfer functions from free body diagrams. So I had a free body diagram for the mass, that's one element that had a degree of freedom x attached to it, and then a node w. And I do not want to draw the node where z is. I don't want to draw nodes where a prescribed displacement is set. In this case, that's that bottom one where z, the input displacement, is set. So I have those two free body diagrams that I can draw together. I want to be careful wherein especially I have springs and dampers that are attached to two non-stationary degrees of freedom like we have in K1 and C. So I completed those free body diagrams and used those free body diagrams to write two equations of motion, one for each degree of freedom, and each free body diagram had one degree of freedom attached to it for this example. This is in the time domain. I rewrote them in 1a and 2a to just distribute out that constant term. I didn't really have to do that, but I like to separate out all of my variables this way. Then for 1b and 2b, I took the Laplace transform of those expressions. W, x, and z are all functions of time, so they are affected by the Laplace transform. So 1a goes to 1b. I had all zero initial conditions because we began at equilibrium. So x0, x dot 0, w0, w dot 0, all were zero in this case and don't appear after that Laplace transform. So 1b and 2b, I now look at them and look at the dependent variables. I counted up the outputs, things that we don't control directly, but we're searching for. That's the displacement x and the displacement w. So here, capital X, capital W, and then what the inputs into the system are. Here, the input, what's prescribed is z, which is a displacement, the height of the terrain we're traveling over. So two outputs, and we have two equations, 1b and 2b, so we will be able to get the transfer functions we want. In this case, only one, we want x over z. So using Mathematica, putting 1b and 2b together and solving for our outputs, and doing a little bit of rearranging, I was able to get the desired transfer function I'll call it G, but that is this X output over Z input. And finally, I had to just write it in descending powers of S to get it into the standard form we want for transfer functions.